Hey guys, so continuing on with 10.4, we're going to do an example of rotating. So we're given this equation here. Looks like it's probably the equation of a circle. And we're told that it's been rotated, or we're rotating through an angle of 45 degrees. So we want to get that new x and y axis. We want this equation in terms of that new x and y axis that's rotated 45 degrees. So we're rotating the axes themselves 45 degrees. And so what we're going to do is we're going to use those formulas that we found in the last video, these formulas here, to get this equation in terms of x prime and y prime. So the first thing we're going to do is we're going to find cosine of 45 degrees and sine of 45 degrees, which we know is square root of 2 over 2 or 1 over square root of 2. For the sake of simplicity in these, we're going to use the 1 over square root of 2 form. And I know we never do that because we always say we have to rationalize the denominator, but in this case, it's going to simplify. It's just going to simplify our math a little bit when we're simplifying the equation. It's going to simplify the simplification if we just do 1 over the square root of 2. So that's the form we're going to use. Instead of square root of 2 over 2, we're just going to use 1 over the square root of 2 because it's simpler. Anyway, so in other words, if you're finding sine and cosine, don't rationalize the denominator in this one case. So that being said, we're going to plug in square root of 2, or 1 over the square root of 2 in for cosine of 45 degrees and 1 over the square root of 2 in for sine of 45 degrees in both of these equations. So in the x equation, that's going to look like this. So we have x prime times 1 over the square root of 2 minus y prime over 1 over the square root of 2. So that simplifies down. The denominator is the same, so that simplifies down into x prime minus y prime over the square root of 2. Same thing's going to happen with the y equation, except for it's plus this time. So we're going to get x prime plus y prime over the square root of 2. It's not always quite this clean, but because it's 45 degrees, and so cosine of 45 equals sine of 45, it makes it a much cleaner. Anyway, moving on. So now we have an equation for x, we have an expression for x, we have an expression for y. So we're going to plug those into our original equation we were given. So we're given this equation, and we're going to plug in this for x and this for y. So we have, instead of 2x squared, we have 2x prime minus y prime over the square root of 2 squared. And then we had minus xy, so we have our x expression times our y expression plus 2y squared, so 2 times our y expression squared minus 30 equals 0. And then we're just going to simplify this down. So we're going to have to FOIL this out. And then, of course, square root of 2 squared is just 2, so we're going to have 2 in the denominator. We're going to have to FOIL this out. This is a difference of squares, so we're going to end up, that's shown here, we're going to end up with a difference of squares. Here, we're going to have our perfect square trinomial. And here, again, we're going to have our perfect square trinomial, but this one is positive, right? That middle term is positive. Here, the middle term is negative. Minus 30. So the 2's in the denominator, so all these square roots are going to end up being squared, right? Because we're multiplying square root of 2 times square root of 2, and then these are squared. So here, where we have 2 out in front, it just so happens that this is 2 and this is also 2. So those are going to cancel. So that's what's showing here. And then we have a negative 2x prime y prime and a positive 2x prime y prime. So those are going to cancel. So we have x squared plus x prime squared plus x prime squared. So that's 2x prime squared, y prime squared plus y prime squared. So 2y prime squared. We still have this term, and then equals 30. So here what they've done is they've multiplied both sides by 2 in order to get rid of this denominator, which makes perfect sense because you can't do anything until you get rid of the denominator. So they've gotten rid of the denominator. Alternatively, you could have done 1/2 x prime squared minus 1/2 y prime squared, and then just dealt with the fractions. That would have been fine. But in order to get rid of the fractions, the best thing to do is always to multiply by the denominator on both sides. And then you don't have fractions anymore. So that's always a good rule of thumb. So then we just have 4x squared plus 4y squared. I'm going to stop saying prime because I'm stumbling over all of my words. And then x squared minus y squared. And this is minus, so we have to distribute that negative. We now have 60 on this side as well. So we have 4x squared plus 4y squared minus x squared plus y squared. So we end up with 3x squared plus 5y squared equals 60. In order to get this into standard form instead of being in general form, which is what we want, especially since it's centered at 0, so it's very easy to do. We're going to divide both sides by 60 so that we have a 1 on this side, right? And now this is in standard form of an ellipse. So we go ahead and simplify, and we have standard form of an ellipse. Now, if these numbers had turned out to be the same, then this would have been a circle. But it didn't, so this is an ellipse. So remember at the very beginning I said, where was it? I said these are both 2. That looks like it might be a circle. It's not. It's an ellipse. So that's why I said when you have that xy term, you can't actually be sure. Well, there is a way to be sure, and we'll talk about that later. But for now, you can't be sure. So this is our solution. So this is the equation based on these axes, not these axes, right? So this is a rotation. This ellipse, essentially this ellipse on the regular xy axis was rotated 45 degrees, and now it's on the xy axis. Yeah. So that, if the question asks to get rid of the xy term by putting, so we're putting the new equation, getting a new representation of this equation by getting rid, and we're getting rid of that xy term by getting it in terms of a new set of axes. That's what we're doing in this equation, or in this example. So what if we're not given the angle? So here we were given the angle is 45 degrees. Well, we can find the angle using this equation here. Cotangent of 2 theta, theta being that angle that we've rotated by, is going to be a minus c divided by b, where a is the coefficient of the x term, c is the coefficient, the x squared term, b is the coefficient of the y squared term, and b is the coefficient of the xy term. Yeah. So we can find out what our theta is by using this equation. Alternatively, if you wanted to rotate something a certain number of degrees, you could figure out what your B needs to be by using this same equation. You just put the number of degrees in there, your A and your C there, and then solve for B, and you'd be able to figure out what B would rotate your equation the number of degrees that you want. Maybe. It might actually be a little bit more complicated than that. I might have to think that through. Yeah, I might have to think that through. I might be wrong. We'll see. They don't actually teach you how to do that in this chapter. It seemed super obvious when I was saying it, and now I'm second guessing myself. So I'll think that through and get back to you on that. Anyway, so going in the direction they're actually expecting you to go in, where you use A, B, and C to find theta, let's talk about that for a minute. So in this example, we're given an equation, and we want to find the same equation, but in terms of x prime and y prime, but we're not given theta, so we need to use this equation. So plugging in our A, B, and C, we get that cotangent of 2 theta equals 3/4. We can just use a calculator to find theta. That would be fine. Oh yeah, one thing I forgot to mention. We need to know what quadrant we're supposed to be in. If cotangent of 2 theta is positive, then theta is in the first quadrant. If it's negative, then theta is in the second quadrant. And if A and C are equal, in other words, if cotangent of 2 theta is 0, then theta is 45 degrees. Okay. So this would be 2 thetas in the first quadrant, 2 thetas in the second quadrant. So theta being 45 degrees would be 2 theta being 90, right? So it makes sense that then theta would be 45. Okay. So that being said, we got a positive cotangent of 2 theta here. So our 2 theta is in the first quadrant, which means theta is automatically in the first quadrant. But anyway, 2 theta is in the first quadrant. So we have different options. Drawing yourself a triangle is a good start. This is a 3, 4, 5 triangle, or you can use the Pythagorean theorem to figure that out. But this is a 3, 4, 5 triangle. You can just do inverse tangent of 4/3. That will give you your 2 theta. But it's going to be approximate, right? You're going to have to round. You could have some rounding error. So it's doable, but if you want an exact answer, or if you're asked for an exact answer, you're going to use the half angle formula that we talked about a long time ago. Half angle formula to get your sine theta and your cosine theta. So half angle formula uses cosine 2 theta. So cosine 2 theta would be, of course, 3/5. And then using that half angle formula, you can find sine of theta. Remember, we want sine of theta, not sine of 2 theta. We need sine and cosine for our formulas here, right? So you're going to find sine theta, find cosine theta, and then do the same process that we talked about in the last example, where you're plugging in that cosine theta and sine theta into these equations. So you're getting your expression for your x and your expression for your y, plugging that into the equation, doing all of the simplifying. So basically, getting the exact numbers instead of a decimal approximation just makes your simplifying cleaner. Because instead of some decimal here that you're not 100% sure is actually 5 when you square it, you know that you actually have 5 when you square it because you didn't round, you had the square root of 5 here. So if you'd gotten a decimal, then again, it would be a decimal. And so you're not sure if you have rounding error or different things. So if you get the exact answer, you just get rid of the uncertainty of rounding error is basically the good side of getting exact numbers here. You're going to do all of your simplifying, and last step, of course, being to divide by the number over here so that you end up with a nice, clean, standard form. And once again, this is an ellipse. That does not look like a 45-degree angle. I suppose it could be, but it looks like less than 45 degrees. Oh, this is the other example. This wasn't 45 degrees. So we never actually found out what 2 theta was. So this is fine. Sorry, I got confused from the last example. We don't actually know what theta is because we never figured it out. We could have. You just, put the inverse in your calculator and you could find that out pretty easily. But this is what you would get from this equation with the new axes, right? Okay. One last real quick thing I want to talk about. And that is how we know what the equation is. If it has a XY term, how we figure out what conic it is without actually doing all of that work to change axes. And that is using the discriminant. Okay, so remember back to quadratic formula, we had this thing called the discriminant b squared minus 4ac. So we're going to use b squared minus 4ac again. So the discriminant, b squared minus 4ac, and again, this is a, b, c, right? And you can ignore d, e, and f. So b squared minus 4ac, if that's negative, then you have an ellipse. Or if a and c are equal, then it's a circle. Maybe. Never mind, because that one example wasn't a circle. So maybe you can't tell the difference between a circle and an ellipse, but you can narrow things down. If you get 0 when you do the discriminant, you have a parabola. If you get a positive number, then you have a hyperbola. So negative, ellipse, or circle. Remember that a circle is just a special case of an ellipse, right? So ellipse could be a circle, could not be a circle. We don't know. 0, it's a parabola. Positive, it's a hyperbola. So that's if you just wanted to know what type of conic you had and you didn't need to go through all the trouble of changing it to a different set of axes, then we can just use the discriminant. So yeah, that's that, and that's all I wanted to talk about. So hopefully that helps. Let me know if you have any questions, and I will see you guys later.